Well, good evening, everyone. Thanks for coming. My name's Samuel Ward, and I'm a research fellow at the Flatiron Institute in New York City, where I've been since October. So today I'm talking to you about an extragalactic murder mystery, and we're trying to answer the question, can black holes kill galaxies? So let's get started, and we're starting right at the beginning, the very beginning, which is the Big Bang. So we think the universe started in this huge explosion, and from this fireball, atoms cooled down into molecules, and these molecules formed stars and galaxies and planets, and everything that we know and love in the universe came to life. And we can track the history of this expansion of the universe by looking at the star formation rate as the universe grew up. So at the start of the universe, we start forming lots of stars. All these galaxies are colliding together, gas is forming into stars. We get this rapid increase in the star formation of the universe. But then at some point, it hits a peak about 10 billion years ago. And since then, it's been declining. So the question is, what is causing this decline? So to understand stars, we need to understand where stars live and are formed, which is in galaxies. When we look out into the universe, we see two main types of galaxies. On the left, you can see these bright blue spiral galaxies. These are the kind of pretty things that you put on a poster on your wall because they're beautiful to look at with these spiral arms. They're blue in color because they have lots of new stars being formed. These sort of little red spots that you see around here are sites of very active star formation. And they're rich in molecular hydrogen gas, which is the raw fuel needed for star formation. The other type of galaxy on the right are these elliptical galaxies. You can see they're much smoother. They don't have these spiral arms. They're gas poor, and they're redder in color because they don't have any new stars shining blue light. So if we have a look over the history of the universe, we can see that at the peak of star formation, a lot more of these galaxies were star forming. But in the present day, there are fewer of these and more of these sort of red and dead elliptical galaxies. So this suggests that there's some evolutionary process that is turning these star-forming galaxies into red and dead systems. And we call this quenching. And the question is, what is causing this quenching? So here I'm pitching it as a murder mystery investigation. This is the crime, that something has killed these star-forming galaxies. And we have a prime suspect. So let's meet our lead suspect. And it is, in fact, black holes. So you might have heard of black holes before. These are these regions of space-time that are so dense and so massive that even light can't escape from it. Many black holes are formed from dying massive stars. And if a black hole forms from a dying star, it will have a mass around 10 times the mass of our sun. So you might think that's pretty big. But the kind of black holes that I study are called supermassive black holes. And these are the ones that live in the centers of galaxies. And these can weigh as much as 1,000,000 or even 1,000,000,000 times the mass of our sun. So these are really huge objects. So something you might think about black holes is, well, black holes might kill galaxies by sucking them all in. So the whole galaxy is sucked into the black hole. But actually, compared to the size of a whole galaxy, these black holes are rather small. And they can only gravitationally influence the very center of the galaxies that they live in. So when these black holes are killing galaxies, it's not through sucking the whole galaxy in. So how are these small black holes able to influence the evolution of the whole galaxy? Well, to understand that, we need to know a process called accretion, which is how we feed a black hole. So if you have a little black hole here, and we want to feed it some gas for it to grow into a bigger black hole, this gas can't just fall directly onto the black hole, because everything in space is spinning. It has angular momentum, and angular momentum has to be conserved. So things can't just fall straight onto a black hole. They have to spin around it. So because this gas is spinning around it, it follows this kind of curved trajectory. And as it goes around the black hole, it gets shredded and is going to form this kind of ring-like object around the black hole called an accretion disk. You can imagine if you've ever seen someone spin a pizza ball, that as they spin it, it gets wider and wider and flattens into a disk. This is this conservation of angular momentum that forms a disk around the black hole. So this is an artist's impression of what one of these supermassive black holes might look like. And when these black holes start sucking in gas like this, they become what we call AGN, or active galactic nuclei, because they're in the nuclei, the very center of galaxies, and they're actively sucking in all this gas. So as this gas is orbiting the black hole, it builds up an incredible amount of energy from all the gravitational forces. And this energy is released in a lot of radiation. These things are really bright and can, in fact, outshine their entire galaxy. There's also a complicated knot of magnetic fields, and this can drive things like jets that get shot out of the galaxy. And these magnetic fields and this radiation coming off can also power winds that sweep through the galaxy, powered by the black hole. So you might think this sounds quite fantastical, but we can actually observe these now thanks to something called the Event Horizon Telescope. So these black holes are really tiny objects. So a normal telescope isn't powerful enough to see it. But by combining telescopes across the face of the Earth, we can actually zoom in to nearby galaxies and see the central black holes. So we've done this twice. This is from a black hole from another galaxy. And we've also done this, the black hole at the center of our own galaxy. And to give you an idea of how incredible this is the same as looking at the moon and being able to see a donut on the surface. So when you look at these orange donut black hole images, imagine that there's a donut on the moon, and that's how far we can zoom in with these huge Earth-sized telescope. So how do these AGN affect galaxies? Well, as I said, all the radiation and energy being emitted by the black hole can power these winds that can sweep through the whole galaxy. We can also shoot very large jets that can reach on scales even larger than the galaxies itself. And we think that these processes affect the star formation in galaxies. So to understand that, I'll briefly explain what conditions we need for star formation. So to make stars, the raw fuel we need is molecular hydrogen. And although stars are very hot, to make a new star, this hydrogen has to be very cold enough to collapse until it's dense enough to kickstart the power production in the star. So if these molecules are moving around too much, they can't collapse. But if they cool down, move around less, then they can collapse and form a star. And this process can be disrupted by AGN in a variety of ways. Firstly, we can just heat up the gas. This means that it can't cool and collapse to form new stars. Or we can eject the gas. We can push it out of the galaxy, so there's none left to form new stars. Or in fact, the intense radiation from the AGN can destroy these molecules, meaning there aren't any left to form stars. So on a galaxy scale, these winds and jets, as they move through the galaxy itself, can be doing this heating, can make the gas turbulent, can destroy the molecules, and prevents new stars being formed. Another important process in galaxies is the fact that to get new fuel for new stars, the galaxies suck in a lot of gas from the surrounding atmosphere. However, if we could heat up the area around the star, it cuts off this new fuel supply. So this will starve the galaxy over long timescales and convert it to one of these elliptical galaxies that have no star formation because they've run out of gas. So this is the picture. Over the age of the universe, the amount of stars has been decreasing as we convert the galaxies into different types through quenching. And one of the main contenders are these supermassive black holes. So we have our suspect, we know our crime. Now let's look at some of the evidence that astronomers use to study this effect. So this is one of the most famous pictures in astronomy. It's the Hubble Deep Field. This is where the Hubble Space Telescope stared at one patch of sky for a really long time. And every speck of light you can see in this picture, and bar a couple of exceptions, are galaxies, even the tiny faint ones in the background. But astronomers don't just like taking pretty pictures. These pictures not only look beautiful, but contain important scientific information. So what can we learn from pictures like this of galaxies? Well, firstly, we can look at the brightness of different galaxies. You can see some are very faint, some are brighter. That could tell us if they're nearby, far away, if they're producing a lot of stars, so they're bright, or if they're producing fewer, so they're less bright. We can look at the shape of galaxies. You can see the one in the bottom right has these beautiful spiral arms, with some of the others of this smoother morphology. And then we can simply count different numbers of galaxies. You can see here there are 3 elliptical galaxies. You can see a couple of spiral ones at the bottom. So understanding the different ratios and numbers of these types of galaxies is very important. We can also look at the color of galaxies. You can see some are blue, some are red, and this gives us important information. So how do astronomers actually take pictures? Well, it's actually very similar to taking a picture with your camera. So say you're out and about and you see a very cute dog and you want to take a picture. This is what your camera does. It splits the light into different pixels. And then in each pixel, it counts how many photons from the dog hit that particular pixel. And by counting up these pixels, you can then recreate the image. However, just by counting the pixels, it will just create a grayscale image, as you can see here. So what we need to do to create a full color image is measure the pixels that get through different color filters. So it's like wearing different colored sunglasses. As you put them on, you can see different colors that pass through. And by counting the colors in these different filters, we can understand the full color information of the picture you want to take. Actually, your phone does this in a very clever way. Rather than taking separate pictures through different filters, it has something called a biofilter, where you can see that the filter is in this sort of a patchwork shape, where some areas are red and some areas are green and blue. So it actually splits up the light into these different images that each contain different light information. And then the image is reconstructed by the phone guessing in the gaps that you can see, guessing where the image would be. So this is great because it allows you to take a picture quickly and really conveniently. For astronomers, this isn't the best kind of filter because your phone is having to do some kind of estimation to see where the light was lost. So astronomers do actually take images with filters separately, one at a time like this. And for example, in the James Webb Space Telescope, this is what the filter wheel looks like. So you can see there are lots of different filters of different colors, and this will rotate in front of the camera to give us a good idea of the different colors of galaxies. So what we can do is we can take a picture like I showed you, and we can measure the colors of different galaxies. And by looking at the differences between these filters, we can quantitatively determine what color they are. For example, the galaxy on the top left, it shows up very strongly in the red filter, but is much weaker in the blue filter. So this would mean that its quantitative color is on this top red end. And if we do this for a whole population of galaxies, we can see where they would fall on this diagram, where we put color of red to blue on the y-axis, and then plot the total brightness of the galaxy on the x-axis. And we can see that this separates nicely into two main populations, and then these green valley that crosses between them. And this actually maps onto the different types of galaxies I mentioned earlier. So these blue galaxies have a lot more star formation, and these red galaxies don't have any more star formation. So simply by taking a picture and looking at it in different colored filters, we can start to understand more about the properties of these galaxies. And on a population level for millions of different galaxies, understand the processes that are happening inside them. But this isn't the only thing we can do with light. So the technique I just described by just counting pixels in different filters is called photometry. But if you ever looked at the sky and seen a rainbow, you're actually doing a science called spectroscopy. This is where we can split white light into every color of the rainbow and study it that way. So if we split up pure white light, we get this continuum where longer wavelengths of light look increasingly red and shorter wavelengths look blue or purple. And these shorter wavelengths actually have the most energy in them. So this is a really powerful technique because of how atoms are structured. So for example, this is a hydrogen atom, which has one proton and one electron. Now, depending on how much energy this electron has, it can occupy these different shells within the atom. So if we give this atom some energy, the electron will be at a higher shell, but then at some point it will fall back to a lower shell, and it will release this energy as a photon of light. And so if it falls from a higher shell, it will release a different amount of energy. And because energy directly maps to the color of the photon, we'll get a different color of photon escaping. So what this means, if you heat up some hydrogen and then look at it, you will see these clear, distinctive lines because of these discrete energy bands within the atom. And so you can see for hydrogen, there's a very strong red line, which is the first band, and you can see the various blue lines also happening as these electrons are dropping down between these different energy levels. If we have a different atom, for example, helium, which has two electrons in it, we get increasingly more options of where the electrons can drop down. So you can see we get a different pattern of lines within a helium atom. And this can get increasingly complex. For example, here's a neon atom, which has a lot more electrons. You can see all these lines, and it gives neon a very distinctive red color, which you'll have seen if you've ever seen a neon sign. And in fact, every atom has its own unique signature of these emission lines, which are like a unique fingerprint that these atoms have. This is an incredibly powerful technique because we can look at a galaxy. This red blob in the top is a galaxy, and you might think it looks like a boring red blob. But when we split the light using spectroscopy, we can see these emission lines from all the different elements. So for example, you can see some oxygen, which is highlighted by the blues, and neon in green, lots of hydrogen lines. And so by splitting up the light, what looks like a red blob actually becomes a rich source of information about what different kind of elements are within this galaxy. Spectroscopy is also a powerful technique because it tells us how the gas is moving. So you might be familiar with the Doppler effect. For example, if a police car goes past you, As it approaches you, you'll hear it at a higher pitch. And as it goes away from you, you'll hear a lower pitch. And this is called the Doppler effect. We also see the same thing with light. So we might have a particular emission line, for example, in the top right of your screen. And if the gas is moving towards us, this line will shift towards the blue side. And as it moves away, it will shift towards the red. Because we can go into a laboratory and measure gas when it's stationary, we know exactly where this line should be. So if we see this line moving, then we know that there's some kind of motion of the gas. For example, in a galaxy, this is really useful. This is a spiral galaxy that we're seeing edge on, and this whole galaxy is rotating. And we know it's rotating because we can look and see at different points along this galaxy how the emission lines are shifted. So to the left of the galaxy, it might be moving towards us. This would then shift the line towards the blue. On the right of the galaxy, it's moving away from us, shifting the line towards the red. So we can look at different places of this galaxy and understand how the gas is moving up towards or away from us. Or we can combine all of this and just have a single line for the whole galaxy. And you can see that it would broaden out the intrinsic line that the gas would normally give if it was all stationary. This is very useful for studying AGN because, as I mentioned before, AGN can push gas very quickly out of the galaxy. And as this gas races towards us, it will produce a strong blue shift from just this gas. So if we just take a single emission line, which would normally give us the dotted shape at the bottom if it was stationary, we can see that it's broadened by the galaxy rotating. And also we have a blue wing of the line that's broad and moving very quickly as the gas is shifted towards us. So this is a really powerful technique. Another way that we can understand galaxies using this idea is because the universe is expanding. This means that galaxies further away from us are moving quicker. So if a galaxy is further away, it's older, it's moving quicker, and it's at a greater distance. So if we have a galaxy nearby, the emission line will be at the rest wavelength that we can observe in stationary gas. But as it moves further away from us, as we look further at older galaxies that are moving quicker, this line shifts. And this is called redshift. And this allows us to accurately measure the distance to galaxies because we know how fast they're moving as the universe expands. So for example, this is a beautiful image from the James Webb Space Telescope. And we can highlight 4 galaxies here that are getting older as we move down. And you can look at the spectra of each galaxy, and you can see that these distinctive oxygen and hydrogen lines are moving to the right as the galaxies are getting older and older, showing they're moving further, moving faster and faster because they're further away. So these are 2 powerful techniques that astronomers use to study galaxies. So photometry, where we just take pictures of a lot of galaxies, this is very quick. We can get a lot of information about a lot of galaxies. And if we do this in different color bands, we can get an insight into the different galaxies' properties. However, we can only get a rough estimate of the distance, and we can't understand exactly the elements within each galaxy. Using spectroscopy takes longer per galaxy, and it's more difficult to build these instruments, but it allows us to understand the gas composition in galaxies and also how it's moving. This also allows accurate measurements of distances to these galaxies. But of course, we can also do both at the same time. So this, again, is the James Webb Space Telescope, and I've shown you the diagram with the instruments attached to it. So James Webb has 4 main instruments that you can see here. And some of them, like NIRSpec in the top left, are just specialized on one technique. Like NIRSpec is just doing spectroscopy. But other ones, such as NIRCam or MIRI, also have photometry attached to them. So we can combine these techniques to study galaxies and especially study galaxies around black holes. So on the left is this beautiful image of lots of galaxies interacting together. And we could zoom in on one and see that there's actually a black hole in the center of this galaxy. And then we can use spectroscopy to understand how the gas is moving around the black hole, and also what type of atoms, which are along the top, and also molecules as these atoms are combined together exist along the bottom. So by combining these techniques, we can really powerfully study galaxies and the black holes that might live within them. It gets even more exciting because out of all the light we can see, this is only a very small amount of the entire electromagnetic spectrum. So if we build telescopes that don't just look in visible light, we can understand even more about galaxies. For example, this galaxy is called Centaurus A, and if you looked at it with a visible telescope, or just looked at it through a telescope with your naked eye yourself, this is what you would see. So there's sort of a spherical white bulb in the middle, and it's covered by some dust that's going in front of it. However, we can use different types of light with different kinds of telescope to study different effects that are happening in the galaxy. For example, we can look in the infrared, and then this dust really pops out because the infrared is showing whether dust is hot. We could use X-ray telescopes. X-rays pick up star formation, which are the little dots, but also start showing you the bright AGN in the center and also a stream that's going towards the top left. And then we could use radio telescopes to see the stream is actually a huge jet that's being shot from the center out either side of the galaxy. And we can combine this all together and shift it into wavelengths we can see to get these composite images where this one picture crams all this information from the entire electromagnetic spectrum into one image of this galaxy. So we can understand the starlight, we can see the dust emission, and we can see the jets being shot by the black hole. So by combining all this information together, we can get a really good idea of what's happening in this galaxy. So that's some of the observational evidence that we can use to study these galaxies. But there is a problem. These black hole murderers have an alibi. So if we go back to this galaxy, these things are really huge. For example, one of these jets is 200,000 light years long. Now, a light year is how far light travels in a year. So to see this jet start from the center and reach the length it would take today, you'd have to wait and observe it for 200,000 years. Now, my career is definitely not going to be that long. So if I look at this galaxy, I can only see it at one single snapshot. It's frozen in time from our short human perspectives. And this makes it really hard to understand how the galaxy is changing and evolving because we can only see it as a static image. It's like trying to understand the plot of a movie, but you only have one still from it. Now, there is some hope. For example, you could watch a lot of movies, and you could discover that in general, stories have a structure. They have a beginning, a middle, and an end. And so you could see, for example, the beginning, you normally meet some characters, they go on a quest in the middle, and the end, they end up defeating the bad guy. And you could watch lots of movies and build up a really good picture of how these things evolve. But you're still limited that you can never watch one movie from start to end. You just have to watch lots of movies, but each one you only see one image from each thing. And it's like that with galaxies. We see these galaxies just at one snapshot in time, and we can start to understand and build up an evolutionary sequence of how they might change, but we can never, from a single galaxy, press play and watch the entire movie. This leads to some difficulties. So, for example, I've told you that black holes kill galaxies. So do you think we're more or less likely to see these AGN in bright star-forming galaxies or in the dead elliptical galaxies? It's actually not what you think. We're more likely to see these AGN in the bright star-forming galaxies. And this might be counterintuitive, that the black holes have fled the scene of the crime. But as these galaxies are evolving over time, both the black hole itself and the galaxy need a gas supply to fuel it. So as the black hole is removing the gas in the galaxy, both the black hole and the galaxy get fainter and fainter together. But because we can only see single snapshots, we might see a snapshot where both the galaxy and the black hole are bright. But then for a different galaxy, we'd see a snapshot where the galaxy is dim and the black hole has disappeared because there's no gas. So it's really hard to see a black hole in the action of killing the galaxy because of this timescale issue. So that's the alibi for the black hole. Have they got away with it? Will we ever be able to understand the evolution of a whole galaxy? So what we need, and would be really nice, is to look at a galaxy like this and to be able to press play and see it move and evolve. And this is another powerful technique that astronomers use called simulations. This isn't a real galaxy. This is a galaxy that we've created in a computer. And then this allows us to track its whole evolution as we press play and run the physics forward in time to see how we think the galaxy might evolve. So how do we build a galaxy in a computer? So first of all, we need the background. And the background for galaxies is formed just after the Big Bang. So this is what's called the cosmic microwave background. And this is formed about 400,000 years after the Big Bang. And it shows tiny fluctuations in density. So the kind of red spots are where the universe is slightly more dense, and the blue spots is where it's slightly less dense. And as the universe evolved, these more dense patches are where the galaxies started to form. And we can go and look at loads of galaxies today and look at their distributions. And you can see that they form these kind of clumps and filaments at the sites of where the initial cosmic microwave background was denser. So this provides sort of the background for building the galaxy, the cosmology that shows us where the galaxies will form and where the gas will be densest. Um, and then we need to understand how the gas moves. And the only force that acts on these kind of large whole universe scales is gravity. So gravity attracts all these different objects together. And on large scales, this is what starts to bring the gas through these clumps to form galaxies. Now, as the gas comes into the galaxy, the gas starts colliding with each other. It means it can transfer energy and temperature to other molecules. And this means that on kind of galaxy scales, this gas can be described as a fluid. And this is why when you look out and study lots of different objects, you might see a similar shape. So, for example, a whirlpool down your plug hole, you might think it looks like a hurricane. You might think that looks like a protoplanetary disk. These are disks around other stars where we think planets form, and which also looks similar to a galaxy. It's because in all of these systems, we can understand how the gas is moving because it acts like a fluid. And we understand fluids very well mathematically. And so we can study them and run computer simulations of them. And this is called computational hydrodynamics or computational fluid dynamics, and is a huge field across lots of different sciences. And it has a lot of real world applications, for example, understanding wind turbines, aeroplanes, cars, and even climate modeling. Because a lot of things in the universe we can understand by treating them as a fluid. So we have the background of the cosmology. We understand how gravity is forming the gas on large scales. And then within these galaxies, we can treat them using these hydrodynamic equations that we know very well from studying them on Earth. And to actually study this in a galaxy, we need to split up the gas into lots of little particles. And these represent a whole parcel of gas that's moving within a galaxy. There are some other recipes that we need to put into this cookbook for a galaxy. For example, we need to understand how this gas is cooling. So hot gas can release energy through radiation and then cool down into cold gas. So we don't, in generally in these simulations, we don't directly model the radiation that escapes. So we have to have some estimation of how much energy is escaping so we can cool the gas down by the same amount. We also want to form stars in our simulations because we know that galaxies form stars. But because within a galaxy, we can't track every single atom, we're just tracking big blobs of gas. We create some kind of model that says if this gas is under certain conditions, such as it's cold and it's dense, then we create stars there. Stars, also like black holes, feed back onto the regions around them by launching winds back into the surrounding medium. So we also need some model for how this gas interacts with other gas around it as the stars are formed. And finally, we need a model for the supermassive black hole in the center. This will both suck in surrounding gas in these accretion disks, but also launch winds and jets back into the galaxy. So these are all the ingredients that we need for a galaxy simulation. And these simulations can be really incredible. This is one example, the illustrious TNG simulation. And these tiny little bright blobs of gas you see are actually individual galaxies. And you can see the long filaments of gas that on these large universe scales are falling onto the galaxies. The galaxies are moving around, interacting with each other. You can see some of them are launching gas back out onto these larger scales. So these simulations are really incredible, allow us to try and simulate a certain section of the universe, run it for the entire life of the universe, and study how thousands of galaxies within these simulations move and evolve. So these simulations, as you can see on the left, are really good for studying these large-scale structure formation as the gas falls along these filaments, and then they form galaxies of these knots. However, a computer is only so powerful, and so there's a trade-off. Do we want to create a really large area to simulate a whole section of the universe? If we do that, then each individual blob that's tracking some of the gas has to be quite large. And this means that these recipes that we put in have to just have a best guess of what's happening within a whole blob of gas. So to try and write these models, we call them subgrid models because they're happening below the grid of the simulation. We need to also understand within a smaller region of the galaxy the effects that are happening. I mean, you can use other simulations to study these effects. So we can use a whole range of simulations at different scales to study the effects that are happening within a galaxy that we can't capture in large-scale simulations. For example, here you can see that as cold and hot gas mix, it cools in a very particular way, and this can't be captured at the large scale at the moment. We can also study how stars are formed. So within a blob of gas, there's actually going to be hundreds of stars forming, each of them with their own interesting interaction of feedback. And so we can simulate just a single blob, understand the stars forming within that, which we could never do on a large-scale simulation. The black holes themselves are also incredibly important to understand. This is a simulation of a black hole shooting jets into the galaxy. These are a much, much tinier scales than a whole galaxy and also need a lot more complicated physics, such as general relativity and radiation feedback mechanics. And another thing we can do is study as the wind or the jet from the black hole races through the galaxy, how it interacts with gas on scales much smaller than can be captured in these large-scale simulations. And this is actually the focus of my own work. So the question I've been asking the last few years in my research is how does how clumpy the gas in a galaxy affect how the AGN can impact the rest of the galaxy? So you can see some different cases on the left. Maybe the gas in a galaxy is very smooth. How would that affect the wind going through it? Or maybe the gas is clumpy, but has different size clumps. And in my research, what I discovered is that when the wind hits these small clumps, they actually shatter into even tinier fragments, which are on really small scales and can be blown out of the galaxy. This has important implications for how cold gas can survive as it's being blown out of the galaxy. And remember, cold gas is where stars are being formed. So understanding how the cold gas moves around the galaxy and how it's affected by the AGN wind is incredibly important to understand where stars might be formed in the future or whether these black holes can completely shut down the star formation in a galaxy. Something else I've been thinking about is how we could study this effect using X-ray telescopes. So you can see on the top right a whole galaxy where we've put a wind through it. And you can see that as the wind races through the galaxy, it shines bright in producing X-rays. And you can see that in a single cloud along the bottom, these X-rays come in sort of a tail behind the cloud. As the wind sweeps material from the cloud behind it, this creates the perfect conditions to see a lot of X-rays. We can study this using X-ray telescopes, such as the Chandra Space Telescope. Or there's future X-ray telescopes that we want to build, such as AXIS. And doing this kind of simulation research can justify whether we can build these new telescopes or not. So this is the kind of scientific process. We build these huge simulations where we try and study the whole universe at once. We can then compare these to observed galaxies to see where our models are accurate at reproducing what we see in the real universe and where they might fall down. We can then use more detailed simulations of just experimental setups or on much smaller regions to build physical understanding. And then from this physical understanding, we can improve the models that we put into the large-scale simulations to more faithfully reproduce the observations. So this is I guess, the whole case for the prosecution. We know that galaxies are being killed somehow, possibly by these black holes. I've discussed the observational evidence that we can use to study these galaxies, but also why observations are challenging because we can only see single snapshots at a given time. So I then showed you how simulations can be run to allow us to study the time evolution of these systems and how we need different scales of simulations to study different effects. But now, and as in any good courtroom, we need to let the black hole speak for itself and start the defense. So if you've ever been outside on a really dark night, you might have seen the Milky Way, our own galaxy, cross the sky. So given everything I've told you about black holes being scary galaxy killers, you might be worried to find out that our own galaxy contains a black hole in the center. This is the image taken with the Event Horizon Telescope that I showed before of the black hole in the center of our own galaxy. And we know this black hole has in the past had a very real impact on our galaxy. Using X-ray and gamma ray telescopes, we can see these big bubbles that it's blown out through a wind or a jet. And that's interacted with our galaxy. However, maybe this isn't as scary as we think, because black holes aren't the only scary things in galaxies. In fact, arguably, star formation is a much bigger threat. When stars are born, some of these stars will be very massive and they will explode as supernova. And when these supernovae explode, they scatter the surrounding region in very dangerous radiation and throw a lot of winds and stuff into the local region. And if this radiation were to hit Earth, this would not be good for life as we know it. So actually, living in a galaxy with a lot of star formation would probably be a bad thing for life, because these supernovae going off would destroy life on planets. So if we go back to this plot, when star formation is peaking in the universe, we have a lot of supernova going off. This is really good for making planets because supernova produce elements that you need to make planets, like metals and dust, and these will later form into planets. So having a lot of star formation in the galaxy is really good for making planets, but it's probably very bad for life on those planets because the supernova will be irradiating the surface of the planets and making it very challenging for life to live. However, in the current universe, where the star formation rate is a lot lower, and even our own galaxy, where the star formation rate is fairly low, perhaps this is better for sustaining life. So maybe these galaxies killing the black holes, killing the galaxies is not such a bad thing after all. So there we go. This is the summary of my talk. I've shown how black holes can kill galaxies, how we can study this with observations and simulations, but also maybe why these aren't such villains after all. So it's finally up to you to decide the verdict. Are these black holes the galaxy killers next door, or cosmic neighbors keeping us safe? Thank you.